Okay, so here are a few other topics that I didn't cover in that initial discussion. So you've seen this before in geometry, but complementary angles. So the are just angles whose sum is 90 degrees, or in this case, or pi over 2 radians. So, if we had 50 degrees and 40 degrees, those add up to 90 degrees. So those two angles are complementary. Likewise, if we had pi over 3 plus pi over 6, that's equal to, so you have 1/3 plus 1/6, both times pi. And if you convert those to sixths, you have 2/6 plus 1/6 times pi. That's 3/6, which is 1/2 pi, which is pi over 2. So pi over 3 and pi over 6 are complementary. What's the big deal about? One thing about complementary angles is that they have the relationship between the values of the angles, as we'll see later. That if you say the sine of theta is something, then the cosine of 90 minus theta is the same thing. So let's say that's equal to x. So the cosine of 90 minus theta is x, or the cosine of, if it's in radians, pi over 2 minus theta equals x. So an example would be, the sine of 30 degrees is a half, and the cosine of 90 minus 30 is the cosine of 60, and the cosine of 60 is 1/2 as well. So that's useful. As far as supplementary angles, there's not really the same relationship, I guess, but so supplementary. So what are supplementary angles? They are angles whose sum is 180 degrees, or pi radians. Now, one thing is that you can have more than two angles. If you had three angles that add up to 90 degrees, they would be complementary. And if you have more than two angles that add up to 180 degrees or to pi radians, they're also supplementary. Okay, so since that's something you should have already had before, I'm not going to dwell on it. We defined earlier that the angle in radians was the arc length divided by the radius. And if you rearrange this, you can say that the arc length is going to be the radius times the angle in radians. And that's one of the main reasons for using radians, is that if we use degrees, we have to go through this conversion process. But for if you're using radians, you don't have to. So let's say we have a circle and some radius r. So the radius r, and we want to know, what the arc length is. So let's say it's 1.2 radians. So if that's theta is 1.2 radians, then the arc length is just going to be 1.2 radians times the radius, which in this case we have to specify it. So let's say it's 0.5 meters. So all you do is multiply by 0.5 meters, which would give you 0.6 meters. Because radians they're meters per meter, so you end up with the same units as the radius. The arc length has the same units as the radius, which is meters. So that's how you would calculate arc length. Now, as a consequence, there's this relationship between velocity, angular velocity, linear speed, angular velocity, and radius, and it comes from this. And so omega, which is the symbol we use for angular velocity, is the amount that an angle changes per amount of time. And the velocity is the amount that the distance something travels per unit time. So using these two and this relationship, you can show that the linear velocity is equal to the product of the angular velocity and the radius, just like the linear distance along the circle is equal to the radius times the angle theta. So these are kind of, this s corresponds to v, this theta corresponds to omega, and the radius is just the radius. So if we said if something is rotating at omega equal to 5 radians per second. So omega is the amount of angle in radians per unit time, radians per second. If something is rotating at 5 radians per second at a radius of r equals 0.7 meters, what is the linear speed there? So the answer is v is equal to omega times r. So omega is 5 radians per second multiplied by the radius, which is 0.7 meters. So you get 3.5. Now the radians drop out here because they don't have any units, so you just end up with meters divided by seconds. So the velocity is in meters per second, which is an appropriate unit for linear velocity. Now, in terms of radians, we just represent them two ways, usually some fraction of pi or just as a decimal. Now, as far as degrees, you can go into more accurate measurements beyond just degrees by looking at them in terms of minutes and seconds. So what you have is, for each degree there are 60 minutes. So you take a degree and break it up into 60, and then every minute you break up into another 60ths, because there's 60 seconds per minute. So, but to do these conversions to radians, you have to convert degrees in minutes, minutes, and seconds into a decimal, and then you can do the conversion. Now this example is just showing you, asking you, assume the Earth has a radius of 4,000 miles. Find the distance between these two angles. So the r is, this is the radius, and then this is the delta theta. That's the change in the angle. So what we need to do is find the difference between these two and then convert them to radians, and then we can calculate the distance in this case. So the first thing we're going to do is we're going to take the difference between these two. So how do you do that? Well, if every one was greater than the other, then it would be easy. But in this case, it's not so easy. So it's kind of like you borrow. So what we're going to do is we're going to borrow 1 here. So this will become, instead of 15 seconds, we're going to borrow 60 seconds from one. We're going to take 1 minute here. So make sure I'm doing this right here. 7, okay. So what you do is you're going to, instead of having 15 seconds, you're going to have 15 plus 60, which is 75 seconds. So this has now become 6 minutes instead of 7 minutes. So you're going to borrow 1 minute, which is 60 seconds. So you add that together. So you subtract that, you'll get 5 minus 7 is 8. 15 minus 7, and then you're going to so you'd have to borrow here, but not borrow seconds or minutes. You're just borrowing it to do the subtraction. So you'd end up with 38 minutes, 38 seconds. Okay. Now again, 6 is less than 46. So what you have to do is you have to go over here and borrow 1 degree. 1 degree is equal to 60 minutes. So instead of 66, we're going to put 66 here. So we add 60 again. So that's 66 minutes. 66 minus 46 is 20 minutes. And then we subtract these two, which is 21. So the difference is 21 degrees, 20 minutes, 38 seconds. Now we're going to need to convert this to degrees in a decimal format. So we're going to have 21 plus 20 minutes. There are 20, that's out of a total of 60 minutes per degree. So we're going to multiply 20 over 60. So that'll give us a decimal quantity. And then the next thing we do is we add the number of seconds, and that's divided by 360. So this is kind of like if you had, the decimal form, we have the whole number plus the number of tenths. So the tenths is some number divided by 10, and then number between 1 and 9 divided by 10, and then we add the hundredths place. So here it's a little bit different because we're not using the decimal system. We're using almost like a base 60 type system. Okay, but you can represent any number between 21 and 22 by specifying the number of minutes and seconds. So, if I had 25 minutes and then I added 60, 25 degrees plus 60 minutes. 60 minutes is a degree, so that would simplify to 26. If I wanted to have 59 here and 59 there, that would give me the closest number to 26. So let me just show you here. So if you have 25 degrees, 59 minutes, 59 seconds, what you do is you take 25 plus 59 divided by 60 plus 59 divided by 3600. And you get, so you plug that in your calculator, 25 plus 59 divided by 60 plus 59 divided by 3600, and I get 25.9997222. Okay. So to get any more decimal points here, you'd have minutes, seconds, and I guess I'm not sure what you'd have next. So, but it still goes out to a lot of decimal points. So we do the same thing here. So we take 21 plus 20 divided by 60 plus 38 divided by 3600, and so we get 21.3438 degrees. So that's the decimal equivalent to this other way of representing angular position. So now to convert that, to do this calculation, the calculation says that the arc length is equal to the radius times the angle theta in degrees. So our radius is 4,000 miles. And now all we have to do is multiply by theta in the decimal form, like that. And we have to, we also need to convert this to radians, and didn't do that yet. So you can't just use degrees. That's the problem with degrees. So I'm trying to get this thing to go down. There we go. Okay, so let's so that's theta in degrees. So to convert that to radians, we take 21.3438 times pi divided by 360. So times pi divided by 360, and I get 0.186261 radians. And now we'll plug that into the equation. So once we have it in radians, we can just plug it in. 0.186261 times 4,000. So we get the distance between those two is 745.04 miles. Okay, so that's talking about angles with a little more accuracy, but using minutes and seconds, how to convert them, well, how to do differences between angles, then converting them to degrees, then converting them to radians, then using the formula that says the arc length is equal to the radius times the angle in radians. Okay, so here we have a 2-inch diameter pulley on an electric motor that runs at 1700 revolutions per minute. Is connected by a belt to a 4-inch diameter pulley on a saw arbor. Find the angular speed in radians per minute of each pulley. Find the revolutions per minute of the saw. Okay, so what do we do here? Well, we need to convert the angular speed from revolutions per minute to radians per minute, because that's what they're asking for here, angular speed in radians per minute. So we have 1700 revolutions per minute. They're 2 pi radians per revolution. So you can see the revolutions cancel out. We end up with 10,681 radians per minute. Now that is the speed of the motor, but what's happening here with the belt is that this thing's spinning at so many radians per minute, and when this travels a full revolution, you're going to go to 1-inch radius times 2 pi, so it's going to travel through a distance of 2 pi. 2 pi is the length, 2 pi inches in 1 revolution. Now here what happens is you've got these belts mean that the linear distance traveled is the same per unit time, but because this is 4 inches, it's going to rotate half as much. So let's, I think that's what we have down here. So one way of doing it too is you can think about that if this thing rotates at this speed, then this one's going to rotate at half the speed, because the actual distance the surface travels has to be the same between them. So that since the distance traveled is omega times the radius, this one's going to, because it has twice the radius, it's going to have to spin at half the speed. So this one's spinning at 5,341 radians per minute versus, so what's this doing is it's slowing this belt arrangement is going to slow down how fast the saw spins, and we want the saw to spin at a certain rate based on safety and efficiency and things like that. So this is just to control the speed of the saw blade, or the rotational speed of the saw blade. And then to convert, we need to convert this back, because it said find the revolutions per minute of the saw. So the radians per second, or radians per minute, has decreased by a factor of 2. Hence, the revolutions per minute has also been reduced by a factor of 2. So instead of spinning at 1700 RPMs, it's now 850 RPM. But if you think about the tip of the saw is the linear speed of the saw is equal to the radius of the saw times its angular velocity. So you get 21,364 inches per minute. That's also equal to the So that's the linear speed. They didn't ask us to do this, but I just want to give you an idea of how fast this thing is moving. So that's the linear speed in inches per minute. So if we convert that to miles per hour, first we convert minutes to hours. So we're going to multiply by 60. So in a minute it travels this far, in 60 minutes it travels the product of these two. Then I convert inches into feet. So there's 12 inches per foot. So that's, you divide by 12, and then there are 5,280 feet per mile. So the feet cancel out, and you end up with 20 miles, 20.2 miles per hour. So if you think about getting hit by something at 20 miles per hour, you can imagine what it's like getting hit by the tip of the saw blade. And this picture is, these are blades on a turbine. Actually, it's probably on a compressor blade, and there are different lengths as you go through the compressor, but these things are spinning. And what this is just to tell you is that, you know, when this thing is spinning, you have multiples of these blades. If you think about the inlet to a jet engine, and you know those things are spinning at a high rate of speed, that means that both the angular speed is high, angular velocity is high, but the linear speed at the tip of the blades is really high. So that's just a thing to think about. And these are homework problems that are assigned. These are the problems, but I'm going to give you you can ignore that because I'm going to give you a handout with the homework problems associated with this section.